So let me start with the just formulation of the classical problem. So the classical Isoperimetric problem in Rn says the following, that if we want to look among all convex bodies, so among all convex bodies K in Rn, and we already have seen that by convex body I mean a convex compact non-empty set in Rn with fixed surface area. Then the statement in that Euclidean ball has the largest volume. Okay, so essentially what's the problem here is I could say that if we look at the all convex bodies such that we fix the surface area, and by this I'm going to denote the boundary of body, and by the vertical bar suggests the corresponding measure in the corresponding object. If we fix the surface area, we want to look at the body that maximizes the volume, and the answer is that such body must be Euclidean ball. Okay. So what I would like to talk about, I would like to talk about the reverse question. So what if I ask, instead of maximizing, to minimize the volume? So the question what I want to look at, what body, and I'm going to deal with only convex bodies, so what body has the smallest volume for a given fixed surface area. So essentially I want to consider something opposite. So I want to fix surface area, but now I would like to minimize the volume. And if I look at this question just like that, so if I start thinking what such objects are, there is a small issue with the problem itself, essentially. So the issue is here, so it's the problem is that I can always, for a fixed surface area, I can always find the body which is very close to the flat body, so very flat. So something very thin, so his ball called such body flat pancakes. And the problem is that if my surface is fixed, then I can squeeze it more and more so that the volume is actually going to approach zero. So the issue is not with the problem itself, but with probably the answer that we get here. So in fact, for such question, the answer is in some sense meaningless in the sense that I just get the trivial bound, the zero, right? So then, of course, the next question is, should we give up, or maybe I just do not ask the proper question. Maybe I can change the question a bit in such a way that I avoid having such flat bodies. Okay? And what we can start thinking about, we can start, well, thinking about adding some additional constraints, right? So narrowing down the class of convex bodies. So probably among the all convex bodies it is not that meaningful, but what if I reduce the class? And the first thing what I can start looking at is something simple as just the intersection, finite intersection of balls. So if I start looking at taking the finite intersection of balls, intuitively I might believe that I should avoid having such objects because the restriction on the ball will not let me to go too flat with fixed surface area. So a fixed surface area, then I try to consider in this body. And so let's try the first idea. Consider intersection, finite intersection of balls with the same radius. Okay, so the first simple intersection, if I take two balls and intersect them, then intersection is going to be essentially union of two spherical caps. And this such union is also usually is called length. Or I can increase the number of balls. So I can look at 3 of them and take the intersection and so on. So it turns out that we can actually consider this class. And in this class, we can show that for a fixed surface area, the such intersection of balls that has the smallest volume is indeed just the intersection of two balls, which is this lambda length. So, and that's what we are going to do. But one can show that in some dimension, but no, let's not talk about this, that among such bodies, length has the smallest volume. And it turns out even better, that even more generally, that if I look at this intersection of balls, then they can nicely approximate some bigger class of convex bodies. That will have some restrictions on the boundary, but which also will allow us to consider this question and get actually a meaningful answer. Okay? So let's discuss this class, a more general class. So let's start with the definition. So definition of lambda convex body. So from the start we fix some parameter. So this is the parameter which is going to be responsible for the radius of our ball. So we want to fix the. So we want to take the balls of the same radius here. Then we say that convex body K in Rn is called lambda convex if the following condition holds. So if for any point on the boundary there exists a supporting ball I'm going to denote it as B sub 1 over lambda comma P. So this is the ball that has the radius 1 over lambda and passes through the point P. I'm going to draw the picture, but for now this is definition such that the following condition is satisfied. That locally, so in some neighborhood, the body is contained in this ball. So here for some neighborhood around this ball. Okay? So let's see what it means geometrically. So what this condition implies? This condition says the following: that if I take a body K, so I look at the boundary of it, I take the point P at the boundary, okay? So then there must be a ball that touches the boundary at the point P of some radius 1 over lambda, okay, such that in some neighborhood around this point, there is a neighborhood in which the body lies completely inside this ball. Okay. All right. This is our code. Are there any questions here?
Yes, so from the local property, there's the global property from it?
So you mean from if it touches from below, right? Or
No, if you have this property, because this is local now, right?
yes.
So does it follow that it's also global?
So I'm going to talk about that. Yes. So this is the, as it's stated here, right? This is the local definition. So something happens locally. In fact, we will show that it's actually global, extends to global using the Blaschke-Rolle theorem. But I'm going to show it later today. Okay. So for now, so this is our object. Okay. So again, from intuitive point of view, if we think about just finite intersection of balls, it's kind of believable that there should be a solution to such minimization problem. And this is an exercise to show that such solution exists. It's using the general, just standard techniques and Blaschke selection theorem. But then it turns out that, in fact, we can really solve this problem in some space. So this is based on the joint work with Kostya Drage and myself. So which said the following. So if I consider now, and I'm going to put R3 here, so we can prove the result in R2 and R3, but unfortunately it is still open in all dimensions. But what we can say that, okay, so if we have lambda convex body, and let by L, I'm going to denote the length, so just the intersection of two balls of radius 1 over lambda. So, and L is the length, the intersection of two balls of radius 1 over lambda. Then, if the surface area is fixed, the length has the smallest volume. Right? So this is the main theorem that what we are going to look at, and we are going to prove it in general. There is a work here that, similarly to the classical isoperimetric inequality, one can also describe the theorem in terms of the inequality itself. So one can show that corresponding inequality that captures this, say that the volume of the body K is the surface area squared of lambda described in the following way, where this is again this is the not difficult exercise to show one can compute directly for the surface area and the volume for the lens in the following way. So if I consider the lens, so these are my two spherical caps. Okay, I can introduce the parameter h, which is responsible for the height of the spherical cap. Then in terms of this parameter and the radius of the ball, which is 1 over lambda, one can show that the surface area of the lens is just 4 pi the radius times the height, and the volume is 2/3 pi lambda squared. So directly computing, one can check for the lens and describe the volume as the function of the surface area using condition that the surface areas are the same, and the result of the theorem, one can get this inequality. Okay, so this is the problem. So this is the theorem that we want to prove. Now a little bit of history about it. So indeed here I said that what we're looking here at the only dimension 3, but this theorem is the answer in R3 to more general conjecture due to Borisenko that says that the above theorem is true in R3. Okay, so the general conjecture that you can do it in any space, length should be the lambda convex body, which has the smallest volume under the fixed surface area.
Katya, is there some easy formula? Because you said you apply the Blaschke selection here, just to say if there is a minimum. Is there some easy formula to get a lower bound, which might be really bad, but at least it's not so.
That you can get a lower bound for the volume.
To be able to know if there is a minimum before knowing what it is, right?
Yeah, I'm not sure the easy But you can do the easy result, yeah. You can bound it from above, but yeah, from below, I'm not sure.
Can I ask a question? But is this interface here the same one that one obtains with the multi-bubble problem, incidentally, or it's the angle between the two surfaces is general? That can be whatever.
Exactly, yeah.
Ah, okay.
Yeah. Well, so once you fix the surface area, right, you can get a unique length that corresponds to it.
Okay, but
right, exactly, but
for each value there is
but for each value there is its own length, right? The radius, this parameter lambda essentially controls that, right? Yes. Okay, so the first results which were obtained in this direction were done on the plane, and on the plane it was done independently by Zendendrach in 2014. Okay, and then by different methods, by further Kurusha and Wick in 2016. The result that we obtained the result in R3, but it also gives us the alternative proof of the theorem in the two-dimensional case, and we're going to see it next time. But the general results for the dimension 4 or higher, this is an open problem. All right. So this is the setup. Now I go back to what Karsten said. So if we look at this definition of the lambda convexity itself, this is the local definition. Now it turns out that this local definition is in fact global, and we can also rephrase it a bit in terms of the curvature of the boundary. But for this I need curvature, so let me briefly talk about the curvature itself, and then using that we're going to show indeed why the following conditions is global. So this. So to go from local to global, I need the notion of the curvature. So let's see how I can think about the curvature. So curvature is essentially the parameter that tells me how far my curve is away from the straight line. Or in other words, I can think about it how fast the tangent vector to the curve bends, right? How fast it changes. So from this point of view, well, what we would hope so that if I have a straight line, then the curvature should be equal to 0. If I have a ball, say the smaller ball and the larger ball, so this one has radius r, and this radius has r capital, such that r capital is larger. Then for the ball, its tangent vector changes with the same speed, and the curvature of the balls is just constant and equal to reciprocal over of its radius. And then the smaller, the larger the curvature is, the smaller the circle is, so the faster the tangent vector bends. So what about the general curve, right? So what now if I want to define the curvature for the general curve? So if I look at the general curve.
You're in dimension 2.
Yeah.
Dimension 2.
Here I'm in dimension 2, yeah. I'm going to say about the higher dimension, right? So let's start for now with just the two-dimensional case. So, but in fact, for the ball right in our end, we talk about the curvature, right? What does it mean, the curvature for the general? So if I want to talk about the general two-dimensional curve, then one way to think about curvature is the following. So I take the point on the boundary, and I might find the best circle that fits the most, that captures the most the curvature itself. This circle is so-called osculating circle. And idea is that if I can find such circle that describes the curve here the most, then the flatter this curve is, the bigger the radius of the circle should be, right? So if it approximates the curve well, then the radius should be large if the part of the curve is flat. So then, from this consideration, we would hope to describe the curvature itself as the reciprocal of this oscillating circle. Then the smaller circle is, right, the bigger the curvature is. So then one can introduce the curvature as the reciprocal of the radius of this oscillating circle, which is also called the radius of curvature. So here, rho is radius of curvature. And one can precisely define this osculating circle in such a way, say that it's a limiting circle. So if I take the point here on the curve, I consider the circles that are tangent to this curve at this point, and whose center lies on the normal line, in such a way that if I take the radius large enough, at some point it might intersect the curve at a certain point. But then, the closer this point gets to the given one, the limiting circle in this case is going to be the oscillating circle. So it's a best circle, it's the circle that best approximates the curve at this point. Okay? And in comparison to the tangent line, it essentially coincides here up to the two first derivatives at this point of the curve. So this is one way to think about the curvature. Another way is, as I said, through the tangent vector. So describe the curvature as the rate of change of how fast the tangent vector turns. So another way to look at it, if I take the curve here, and again I choose some point, let's call it point P. At this point, I have the tangent line, then I choose another point Q, at which I also have the tangent line. Then one can move the tangent line at P parallel such that it passes through Q. So then the angle that we have here, I'm going to denote delta theta, is essentially the change of the angle of the original tangent line with respect to this tangent line, the angle between the line and the x-axis. And the curvature then can be defined again as a limit of the change in angle with respect to the distance that we traveled, so with respect to the distance that we traveled along the curve. So, or the change in distance when the point Q gets closer and closer to the point P. Okay, so essentially what the curvature here captures, it captures how much the tangent vector changes over some certain distance traveled. Now, this was about the plane curve. So how to think about it in her dimensions? I'm going to explain in R3, and then one can generalize approach to the higher dimension, but I will need only R3, so I'm going to stop with R3 here. But in R3, so what we can, how we can think about it for the body. Right? So if I think about the body K in R3, then again I can choose the some point P here. At this point P, I have the at this point P, there is a normal vector to the boundary, and then I also have the tangent plane at the point. So in the tangent plane, it's enough to look only at the unit vectors. I can take the circle of unit vectors at this point. So tangent plane here. here, right, let's say that I have just the circle of unit vectors, right? And I choose one unit tangent vector, right? Now I have two vectors, normal and tangent. I can span a plane via them. So these two vectors are in the plane, right? And if I take the cut of the body with this plane, then in the cut, what we get here, we get some curve, right? But now the plane curve, right? The curve that lies in this plane. For this plane curve, I can compute the curvature, right? In the previous way how I want. So I can compute the curvature at this point P, right? Then I change. So then I start varying this plane. So I start taking another tangent vector, right? Take another cut, take another curve, plane curve, compute its curvature at this point, and so on, right? By varying this, my tangent vector, and by varying all these planes, I can choose the smallest and the largest, the curvatures among all those which I found. So let me say that K1, I'm going to denote the smallest curvature, and K2, I'm going to denote the maximum curvature among all such. So smallest and largest curvature among all such, I'm going to call them normal curves. Among all such plane curves that lie in the plane that contains the normal vector. And such curvatures, so K1 and K2, are called principal curvatures. And the directions, the tangent vectors, the direction in which they obtained is called principal direction. Essentially, so what this curvature tells me, so the direction tells me the direction in which my surface bends the most or the least, and the curvature measures how much it bends. The principal curvatures measure how much it bends. And another thing what I need, I also will introduce the notion is important in the three-dimensional case and related to the curvature. So the Gauss curvature, which is just the product of the principal curvatures. So now from this point of view, one can extend the notions of the principal curvatures in the higher dimension, but again, they can be defined as some eigenvalues of the certain operator, but I'm not going to go into that. So for me, R3 here is going to be enough. Now, if I look at this, if I think now about the curvature, and so I raised it already, but look at the definition of the lambda convex body, then what can I can reformulate my condition for now in terms of the curvature, right? Because what I'm saying that I have a body, from the outside of this body, there is a supporting ball, so definitely my body curves more than the ball itself. And for the ball, for example, for the ball, both principal curvatures are constant, right? So if I think about the ball, the Euclidean ball of radius r, right? So both principal curvatures are constant, and the Gauss curvature is also constant, is equal 1 over radius squared, right? So from this point of view, then I can remark that lambda convexity there can be thought in terms of the constraint on the principal curvatures, on the curvature of the boundary of my body. Because I can say now that K is lambda convex if all its principal curvatures at most 1 over the radius, right? So we assume that the radius 1 over lambda, so the curvature is here at most 1 over the radius. Right? So the body bends more than the ball itself around the point P. Okay, so now, as I said, one can also reformulate, so one can also obtain the constraint in the definition, pass from the local to the global constraint. And this is done via the so-called Blaschke's-Roland theorem. So let's see. state equals so-called Blaschke-Roland theorem. So for lambda convex body, so let K. Again, I'm going to state and prove it in R3, but there is a generalization to higher dimension, which requires a bit more tools, but one can do it. So let K be a lambda convex body. Then the theorem says that for any point on the boundary, there exists supporting wall in the same sense as before. Let me again call it B 1 over lambda P, such that now we know that it actually implies that the body completely lies in this ball. Okay, not locally, but completely. So there is a ball that completely contains, there is a supporting ball that completely contains the body. Okay, with the radius 1 over lambda. Okay, so let's prove it. So for the proof, I'm going to complete it in 2 steps. So first I'm going to prove it in R2 and then I extend it to R3. So first step, on the plane, okay? And on the plane I can prove a bit even more general results. I'm going to state it in this term. So let's say that on the plane I have 2 curves, gamma 1 and gamma 2, okay? So be 2 curves. In R2, such that they touch at some point P, okay? So the picture, so I have one curve and another curve, gamma 2, that touch at the point P, and also in such a way that both of them lie to the one side of the tangent line at this point. Okay, so such that gamma 1 and gamma 2 lie to the one side of the tangent. And now I also assume that at every point, but from this point of view. So also assume that at every point, 2 points that have the same normals. Okay, so I'm going to look at the curvature as the function of the normal. So meaning that, let's say that at this point, this is my normal vector, right? So I want to find a point on the other curve which has the same normal vector. Let's say this is the point it corresponds to, okay? So at 2 points where the normal vectors are the same, so assume also as functions of normals at points with the same normal, the curvatures satisfy this inequality. Okay. And then the conclusion is that the region gamma 2, then gamma 1 completely sits in completely sits inside gamma 2, and the regions that they bound also sit inside.
Curvature may not exist, right?
The curvature may not exist, yes. So the points essentially, I'm looking at the points, right? They're, well, what is my bodies are, right? My bodies are, they are not going to have the flat parts, right? So the ball constraint, right, prevents me of having the flat parts. So if it, so for the smooth parts, right, it is going to exist. In general, it's going to exist.
It can have a crisp or
It can have a corner, yes, it can have a corner, right? But it can have a corner, but I think it shouldn't. I think it shouldn't matter, but maybe I'm mistaken. Let me think. Okay.
This is basically the maximum principle. It shouldn't matter.
I think it's really, the corner shouldn't matter. So the problem would be if I have going to have a flat parts, but I cannot have the flat parts. So for that I think I should be okay.
Yeah, a corner would matter if you wanted to put the ball inside. But
Right, but the outside it shouldn't. Yeah, outside it shouldn't matter. Okay. Okay. So let's do this. So how I'm going to prove this? In order to prove this, in R2, I want to use the notion of the support function. Okay, so we already have seen, I know the support function in the last talk, but the support function, this is the function h, let's say at the vector u, this is the maximal of the following here, right? And this is the general definition which holds in any dimension. So this is just the following quantity. What it means geometrically, the following. That if I have the body k, and let's say I have somewhere the origin, let's say the origin inside, doesn't really matter. But what this tells me, what the support function represents, it tells me that if I choose the direction to some vector u, I can find the tangent line or tangent plane with this normal vector to the body k. Let's say this is the tangent with this direction u, and then the support function just measures the distance from the origin to this plane. Okay, so now if I think about this in terms of the support function, what I can do. So first, I think here at the curvature is the function of the normal. So I can always parameterize the normal, right? So I can always choose the look only at the unit normals, sin t, okay, where t is just the angle the normal makes with the x-axis. Okay, so you can always look at such normal, and I can always rotate my picture in such a way that I choose p to be the origin and the normal, so the x-axis, be aligned with the normal at this point p. Okay, so you can always rotate the picture so that p is the origin, right, and so x is aligned with, let's call it normal vector and dot. Okay. So what does it mean in terms of the support function? In terms of the support function, this condition tells me that at 0, the support function is just 0, and this condition is going to tell me that the derivative at 0 is also equal to 0. Again, here, once I parameterize the normal vector with respect to the angle, I can also think about the support function and the function of this angle. Okay, so this is all as a support function of the angle t. All right? So I have these two conditions, and the nice thing, what I know about the support function in R2, that satisfies the relation. So for the support function, what we also know that it satisfies the following differential equation. So that the second derivative plus the support function itself is equal to 1 over the curvature. Okay, so again, one can see that if one computes the support function for the circle such that it touches the y-axis at the origin, one can compute it directly and see that this holds, this is satisfied. And then when we talk about the general curve, then we can always approximate them with the oscillating circles. In some sense, what we only need for that, we only need the two derivatives. And here, where those two, the oscillating circle and the curve itself coincide. So one can believe that this is also true for the general curve too. So we have this differential equation. Now, what I'm getting the initial conditions and the second order differential equations. So I can solve it, and I'm going to leave it as an exercise that one can use just the example variation of parameters to show that the solution here with such initial conditions also can be described in this way. So it's integral from 0 to t 1 over curvature So this is the solution to this differential equation with such initial condition. So another thing, what we know about the support function, maybe let me fit here, that there is also an exercise that can be done that if two bodies K and L related in such a way that K is contained in L, then this happens if and only if the support functions connected in this way. Okay. One direction, this direction is clear, and for the other one can do a simple argument to show. So using that, if I want to show that the region that is bounded by gamma 1 sits in the region that is bounded by gamma 2, what I can do, I can try to compare their support functions. Okay? So this is my description for the support function, and what I know. So if I consider the interval on which from 0 to pi, where of course tau here is less than t, then what I can do. So the one thing, what I have in my condition, that the curvature is related in this way. Right? Now, of course, if the curvature is related in this way, the reciprocals are going to be going to change the inequality. The sign function in the solution here is non-negative on this interval, so everything is good. I can just multiply both sides by the sign function. So and then I can integrate. I can integrate on the interval from 0 to t. So this tells me that, means that the support function of the first, so the body that of the region that is bounded by gamma 1 is at most the support function of the region that bounded by gamma 2, which will imply that the first one sits inside the second. Okay? So this finishes the argument in the two-dimensional case. Now, what I need to extend it to the three-dimensional case. So what I can do in R3 for my lambda convex bodies. So the one simple observation that I can make is the following: that lambda convexity is preserved under taken sections by planes that contain normal vector. Okay. So again, this is essentially follows from the definition, right? So I have a ball that if I start taking the section with the plane that contains the normal, I again going to get a curve which sits inside the 1/λ disk, right? And because since I have the plane that contains the normal vector, the center of the ball lies inside this plane. So, okay, so if I have something lambda convex, I again take the normal, take the plane that contains this normal, right? I get the section, right? So let's say that this is my plane H. So K intersected with H is again lambda convex. Right? And the ball, so the touching ball that we had here at the boundary, right? Its intersection, so intersection of with H is a disk of, again, the same radius, of radius 1/λ. Okay? Make sense? All right. So then, what do I know? By the two-dimensional result, so here's also, right, and there's a disk that touches the curve. So by two-dimensional result, right, I know that how the curvatures here at this point are connected. So by two-dimensional result, I know that this sits inside this disk, right? So the curve sits inside the disk.
It's sectioned by a plane that contains one normal or a plane that contains every normal?
That contains for now this normal at this point, okay? So for now this normal, okay? Because the normal at which there I have this, at the point right where I have this supporting pole, okay? So for this direction, right, I can say that one sits another by the two-dimensional result. So by step one, this it's in this guy, right? But now I start varying the plane again, right? So start varying the plane in such a way that all such sections are going to sit inside the pole, right? So then by varying the plane, H get we get the result. Right? Okay. So this tells me then, well, I have this more general, now my definition implies the more general thing, that in fact, if I have a lambda convex body, then at every point, there is a ball that completely contains the body. And why in particular I need the Blaschke's-Roland theorem? Because Blaschke's-Roland theorem can also help me to obtain the following results. So if I start with a convex body, with lambda convex body, it turns out that I can approximate this lambda convex body with such just intersection of balls of radius 1/λ. Okay? And this is essentially, again, can be done by Blaschke's-Roland theorem here. So if I can approximate the general lambda convex body with intersection of balls, I can deal with intersection of balls first, hope to get the result there, and then extend it to the general bodies by approximation. Okay? So the last thing what I'm going to mention here that the Blaschke's-Roland theorem essentially then gives me the way to approximate the general lambda convex body with the general lambda convex body with just the intersection of the finite intersection of balls of radius 1/λ. The last remark for today that if I have the convex body, then there exists sequence of I of, I'm going to call them now lambda convex polytopes, just by analogy with the general polytope. So this is just the intersection of balls of radius 1 over lambda. Then there is such sequence such that one can even construct a nested sequence of such polytopes. So we can say that this is a nested sequence of these polytopes such that in a limit and limit with respect to the Hausdorff metric, we get the body of K.
Just the radius must be 1 over lambda or also less than 1 over lambda?
The radius should be 1 over lambda, right? So for each fixed lambda here, right? Here, what I have the supporting balls of radius 1 over lambda. So now I say that I'm taking the sequence of polytopes, right? That,
I can imagine that if you have this body K, lambda convex body, at some point the curvature may be less than 1 over lambda, right?
the curvature is always greater than lambda, right? Than 1 over the radius.
Of
Curvature is greater
less
than
1
lambda.
over lambda.
Yeah.
So does it mean that we can also take the balls to have curvature greater than lambda, or?
Yeah, you can. Well, you can touch, right, with the larger ball, but they're always going to be the 1 over lambda, right? This is kind of your the limiting case. Okay, so if we can approximate the general body by this lambda convex polytope, then what we're going to do, we're going to deal with that. So the lambda, the just intersection of balls sounds easier to deal with. So we're going to try to prove the theorem now for that, and the general case will follow by the approximation essentially. The general inequality is going to follow by approximation, okay? So next time I'm going to start, going over the proof of the result and do that.
Okay, thank you.